Greetings.
Good morning.
Geez, Hannah's got glasses on today. It's serious. She's getting serious.
I am.
It's a good thing. I'm going to show you things today that you did not know existed in the universe.
Are we starting a new unit today?
Yeah, we're starting something new today. Well, in a sense. I'm going to show you how to do everything we've been doing using just one method. Got up at 5:30, hit the gym, met a dude about house plans. The day's almost over.
So there's no homework due this week?
Let's see. No, because we're gonna be cruising through Laplace Transforms for a while before that's due. So, nope. We're not done with talking about, like, we have 3 days with, just 7.5. That's kind of the problem. So it's not really due to the end of next week. Isn't that lovely?
Yes.
Yes, that is very lovely. Last week was kind of busy. You had some projects and tests, and so don't you deserve a little bit of a break? I think you do. All right, let's get after it. Technology is working. .2. So I probably will make a few comments about the test, like kind of at after class. Then I have all your tests that I sent you saved. So if you want to, have a discussion as always about, what went wrong or, whatever, certainly would love to do that with you. Let's see, do I have any memories of it? Yeah, anyway, we'll leave that for later. But today we are learning about something called a Laplace, French, Laplace Transform. And I think I introduced you, who was that dude I introduced you to? Was it Euler? Yeah, it was Euler. And one of the quotes was from Laplace, Pierre Simon Laplace. I think it would make sense for me to even give you extra credit to research this dude, Pierre. Probably spell his name wrong. Simon Laplace. So, extra credit, go research the dude and make like a 1-page, kind of like I did with you guys with Euler the other day, make like a 1-page, just what copy and paste out of Wikipedia or whatever's, interesting about this person. When did he live? What did he do? It's just kind of cool, I think, to have some background on this, on kind of who these people were and some of the stuff that gets invented. And, I'm always trying to get across a little bit of the mystery to this. You want this isn't a hard section. I think you'll find this not hard at all. But I'm about to show you what a Laplace transform is. And, it's like, where did that come from? And it's rather a remarkable, kind of a crazy process. But I can explain it super simple. But when it comes down to it, it's really this. Like, let's think about where we've been. We started out with separable differential equations, and we said, hey, we can solve those. Those were first order. They were one derivative. And we said, well, we can solve those if we can separate them. That was like we had something we had to notice, right? And that wasn't always obvious. So it's like we could separate them and we could solve them. And then it was like, okay, well, what about the ones you can't separate with a plus sign? Oh, well, we found this cool mu technique for solving linear. We had to recognize, oh, that's a linear differential equation. And then we can find mu and then mimic the product rule and, solve it that way. And so, it was like two different techniques for two different situations. And then it was like, well, what if it's a second order differential equation? And, you just took your test on that. And that, of course, was really complicated because sorry, the screen went black again. Because you're thinking, oh, is this homogeneous? Okay, we are basically guessing. We're guessing our answer for that. And ultimately, we said the guess was just based on E. And then we saw pretty quickly that the auxiliary equation formed from that. And so that gave us our exponents for E, and that was awesome. But then we moved on and said, well, what if there isn't a zero on the other side? What if there's other messes? And then we saw, wow, that was really complicated and we had to be really good at guessing, and that was all confusing. Well, Laplace transform is like a technique that just solves them all. Just do Laplace transform, doesn't matter what it is. Same exact approach every single time. It's rather brilliant. And because I've at least done somewhat of a reasonable job helping you understand that, these things are a lot of different places, differential equations. And that test question I gave you is really kind of a cool one. We're not, studying electrical engineering yet, but the fact that that's a real equation, and I sort of threw real numbers at you, which is why the answer came out as kind of crazy as it did. That's a real equation that electrical engineers use to manage how circuits operate, voltage, and you might have noticed like all these units you'd never seen before, like farads and henrys, and if you get into electrical engineering, you'll see that. And so these things are lots of places, and we just finished a project where I showed you I guess you might say civil engineering or structural engineering, where we learned how beams work, and you ended up needing to solve differential equation for that. And so ultimately, Laplace transform is just another method to solve them. These exist in the world. They're kind of cool. They model real things, and they're really neat in that regard. But how do we solve them? So in a sense, we're not learning anything new. That's the good thing. I'm not showing you new types of differential equations here. We're just going to take a different approach to solve them. And it really comes down to something that the concept of a transform is really this. This is a really simple illustration, and it totally makes sense. So it's like you see some WWF fighter on TV, and somebody says, well, can you win if you fight against that person? And of course you'd say, well, no, I can't, because they're bigger, stronger, talented, and so forth. But what if you went and transformed them? What if you got in the ring and then you transformed them down so they were an inch tall, and then you stomped on them, and then they got back to full size, and then you won the fight? And that's kind of what we're going to do. We're going to transform. We're taking these problems that we don't know what to do with, and we're going to transform them to something easier. We're going to solve it in that world, and then we're going to put it back into the world we came from and get the same answers effectively that we had before. I mean, that's really the gist of what's happening here. It's that simple. So let me tell you what it is. This is a Laplace transform. What we're going to do is we're usually in time. In other words, our function, I mean, sometimes we had x's, but for the most part, a real differential equation is how something is changing over time. And so our time was our independent variable. And what we're going to really do in this section is change to, we're going to change to a different letter. As it turns out, conceptually, to understand it, you're actually changing from time to frequency. But what we're really going to do is change this to a totally different letter. Now, this is not that unfamiliar to you. When we took an integral, didn't we say, man, I don't know what to do with that? I know what I'll do. I'm going to let u be equal to sine of x, and then I'll make a substitution. And then we got in u land, and we went, oh, okay, now I can solve that. And then we put it back to x's, and we had the answer, right? I mean, you've done this before. This isn't that novel of a concept. All we're really going to do here is just change this. We're going to substitute from t into s, and that will be the transformation. And then we'll solve it in that land, and then we'll switch it back. I mean, it's just a brilliant and simple idea. Now, the thing that is not simple, here's a Laplace transform. The Laplace, and I don't know why, but I'm really happy about it. You'll see in books that it's like a cursive L instead of just a plain old ugly L. And I don't know why, but I just think that's awesome, because this is such a crazy and a cool technique. So if we want to take the Laplace transform of some y of t function, dang, come on, computer, don't fall asleep today. This is important. Then here is what it is. If you take the integral, not from like 5 to 2, which would be what you used to call a proper integral, we're going to take an improper integral. Improper is when you get infinity involved. In other words, the area under a curve from infinity to 0. And again, if you took Math 253, you spent a lot of time understanding that a little bit more deeply. But you can, I'll just briefly say, if you have a curve that looks something like this, and this curve asymptotically approaches the x-axis, and you'd say, I'd like to know the area from x is 2, and you never quit. You go way out there to infinity, as though infinity is a landing place, that you actually can find that area sometimes, not all the time, but sometimes, if the curve approached the graph close enough. So you don't need to have taken 253 to understand what I'm going to show you today, but it deepens your understanding if you do so. So this is an improper integral. So even though you go to infinity, yet it has a finite area. It's just a crazy concept. And then here's what we're going to do. We're going to take this equation, the original equation right here, whatever that equation was, and we're going to multiply it by e to the negative s. There's the s that we're changing it into, times t dt. This, my friends, is the Laplace transform. Now, that's rather magical, right? Like I just threw it out there. Said, here's what it is. Go do it. I'll back up and explain a little bit more about where that comes from. But notice it says e to the negative st. You should understand that, well, that's a negative exponent. So that means that e to the st could move to the bottom. Well, if t, because remember this is kind of important. I think I'm going to even add that in here. These are t's, right? In other words, if it's with respect to t dt, then that's t is infinity and t is 0. Well, if that was, 1 over e to the st, if t is infinity, does it make sense this thing is on its way to 0? I mean, you have 1 over a large number there, right? And again, if you took 253, that's a lot more of a, okay, yeah, obviously, kind of a thing. And so that's at least a little bit of why that's thrown in there. But this is what we're going to do. We're going to take our equation, we're going to transform it into a brand new equation. And notice we have to take an integral to do that. And then we're going to kind of work with it in that land, frequency land, ultimately. And this is going to make amazing progress. Now, this is not something I can explain completely in one session. So, it'll take maybe, what is today, Wednesday? Like by the end of tomorrow, I think you'll begin to have a pretty good feel of how this works. And again, it's not hard. You're all going to get this. This isn't bad at all. But let's just dive in and start thinking about it right now. Let's see, which one shall we do first? look at my table of Laplace transforms.
Hey Doug, have you ever heard of I called it Laplace when I read it, but I guess Laplace's demon. It's just a random theory. And I just wondered if Pierre Simon Laplace like thought of it.
Yeah, that's one of the reasons I'm giving you extra credit for going and searching this up a little bit, because I think he's the one that thought of this. But I sometimes it's got named after them kind of posthumously after they died. And so that's kind of an interesting side of this.
Yeah, I knew that theory along with like Schrodinger's cat and all those other like ridiculous just like thought experiment type things. And when I saw Laplace transforms, I was like, oh, I wonder if it has anything to do with that, but it doesn't seem like it does.
I haven't heard that it does, but that's a road worth running down.
So this is the determinism argument, right? So the if you have all of the possible available information, then you can chart the future from that point onward.
The future and the past. You can know everything in the past and predict all of the future.
Well, let's launch in and try to transform something. So we have an equation like that, e to the at, and a is a constant. That's important to know. But you're far enough along in math that you can treat that like a constant without it being one. And as I've told you before, this is kind of what mathematicians do. They choose the lower letters. Anytime you see A, B, C, D, those are constants, whereas X, Y, Z, those are variables. So in this case, T is changing. So we can't fix T to anything. We can't say, T is time. We can't say time is 2. Because if we do, then time stops and nothing is changing anymore. So T is going to have to keep changing. T is a variable. Whereas A is like 5 or 7 or 9 or 12, but it's permanent. So, you won't be doing this for e to the at. You'll be doing it for e to the 5t. But of course, we just want to do it for every function possible. Okay, so Laplace transform says, so there's our sort of y of t function. So, what does it say to do? Well, it says take the integral from infinity to 0 of that function, e to the at, and then you'll always multiply it by e to the negative st dt. So we've got to take the integral of that mess. And this method depends on you being able to take the integral. And again, I think it's important to note, important enough, I'm going to go back and rewrite and in a different color, that these are t's because we're doing this with respect to t. So t is going to take the value infinity and t is going to take the value 0. Now, as you know, since that is e to the junk times e to the junk, you would say, well, I know how to handle that. That is the same as, well, adding them together. So you can add those exponents. So I could say that's the same as e to the a t minus st. And I think I'll even, I guess I can leave it that way. Since they both have a t, it'd be a t minus st, or I can just say a minus s and then multiplied by t dt. Now the question is, do you see that as something that you can now take the integral of? Now, notice t is the only variable, a is a constant, and we're treating s like a constant. So I'm going to make a note of that because I want to kind of start slow here. A is a constant. We're going to treat s like a constant. And the reason I say that s is not constant, it's a variable, but we can treat it like a constant because we're taking the integral with respect to t. In other words, we're interested in how t is changing, not s is changing. For those of you taking Calc 4, This is kind of hinting at the concept of a partial derivative, where you just say, I'm interested in one thing changing, and I'm going to treat the other one like it's not changing. So S here is not what we're paying attention to. So we're going to treat it like a constant, even though it isn't. Well, you know what the integral of e to the junk is. E to the junk is e to the junk, right? So I can take the integral of that. But we're not done, right? What else is there to do if you take the integral of that? Because of the chain rule.
You had to do a U sub.
Yeah, and it depends how good you are at integration. Really, what you would need to do, I'm going to erase this, but if you said, I'm going to let u be equal to a minus s, the long and the short of it is, you would end up needing to divide by a minus s. So I'm not going to take the time to do the u substitution and so forth. But, you know, as a simple example, just to make sure you're not screwing up. In other words, if I said, what's the integral of e to the 5t? You would say the integral of e to 5t with respect to t, I didn't write dt, is e to the 5t. But then you would need to divide by the derivative of 5t, which is 5. And notice if you take the derivative of that, the derivative of e to the 5t is e to the 5t times the derivative of 5t, which is 5. And then those 5s would cancel. So that's all I did, right? It's not hard. And now I just need to evaluate that from t is infinity and t is 0. Now, I'm going to do one cool sort of tricky little thing. As I said before, if that e to the junk times t, if that was negative up there, then I would be able to put infinity into it and it would go away. In other words, I sort of need the e to go to the bottom. So I want to do something kind of cool here, something kind of tricky. What if I switch this around to s minus a? In other words, I factored a negative out of that. First of all, are you okay that I didn't do anything there, but just some simple algebra? So now it's like e to the negative t, if you will. And I'm still evaluating this from t is infinity to t is 0. So then you say, okay, cool. Well, now then this would be effectively e to the negative infinity. Notice, remember, s and a are constants. So a could be 5 and s could be 12. But if they're being multiplied by infinity, then they're going to cease to be important. Do you agree with that?
Is this, isn't it supposed to be negative since you factored out the negative in the s minus a?
No. If t is infinity, then I basically have negative and infinity, and then I have s minus a.
I meant before you did that. Like, so did you change it? Oh, I think I see what you did. Never mind. Never mind.
I love it. Interrupt and ask questions. So it used to be a minus s. In other words, a was positive, s was negative. I took a negative out, and then s was now positive and a was negative. So I flipped them around. So I really, all I did was just factor a negative. I just factored a negative out of this so that this could be negative.
I thought you did that before you integrated. So I was, in which case you would have had to add a negative to the other side, but you didn't, so it's fine.
Got it. Yeah, good job. So I get e to the negative infinity, which now you understand that's 1 over e to the infinity. And so that's on its way to 0. Do you agree with that? So this is on its way to 0, and it's still over a minus s, but that isn't going to matter. If that goes to 0, then I'll have 0 over some constant, 0 over 50. Well, it's still 0, 0 over 900. It doesn't matter what a minus s is if those are constants. So in this way, that improper integral is actually going to approach something. And then, as you know, then I say, okay, now minus And then it's e to the negative s minus a, but now it's multiplied by 0, right? Because t is 0. So what happens to that mess algebraically?
Just 0. Oh,
Yeah,
and wouldn't it be 1 over a minus s actually? Maybe I'm
yeah,
wrong.
because you have 0 times s minus a. Remember, s minus a, we're treating it like constant, so that could be 50 minus 90 or whatever. It doesn't make any difference. If I multiply 0, this is going to become e to the 0, right? Which is really just 1. So I basically have negative 1 over a minus s. Or if you don't like negatives, 1 over s minus a. So what just happened? We took the Laplace transform and we took the equation e to the at. So it's important to note this is a function of t. That's t's, right? Whatever that function is, it's made of t's. It's made of times. And then it turned into 1 over s minus a. Remember, a is just a constant. But s is the new variable. So in other words, this is like 1 over s minus 3, 1 over s minus 7, something like that. Does it make sense? This is now a function of s. So do you see that we accomplished what I said before? Now, again, this feels, you have no idea what we're doing yet, right? Like you can follow what I'm saying, but you're like, I don't understand what you're doing or where this is going. You shouldn't. We're not there yet. I got to show you quite a few things before I can show you the power of what we just did. So I just transformed this from an e function into, well, I guess you just say, 1 over s is a, what is that, fractional function, or what's the word for that? What's the other mathematical name for fraction? What can I think of that?
Rational.
Rational. Thank you for rescuing me. So it went from an exponential function to a rational function, like for whatever that's worth. Now, again, it's not okay just to do this, right? You can't just go down to the bank and say, I'd like to transform my bank account into times 10. They're not going to let you do that. So it's not okay that I just change this into some other world. It's like saying, you can't handle E, huh? So then you'll make it into something else. Well, it isn't going to work. But the idea is I did change it into something else. And if acting on what I just changed that into makes it easier for me, as long as I change it back, then that's okay. So it went from a function of t to a function of s, whatever the heck that means.
There's something that's sort of bothering me here, which is what if a is bigger than s?
Nice. Explain that a little more, Landon, so people understand that, because maybe that thought did not occur to them.
So a big part of this, of e going to negative infinity and turning itself basically to 0, is that you have to end up with a constant time, a positive constant times negative t to get negative infinity. Because if a is larger than s, then s minus a is negative. Times the negative in the front, we have positive t, and then we are not going to 0 anymore.
Do y'all understand what Landon just said? It's really important, and he's exactly right. And if I could have paid him to say that is exactly the right time to say that. In other words, this going to 0 right here only happened because of that negative sign. You agree with that? Which is why I made a point of making one when there wasn't one, right? Like there wasn't a negative sign there. And I said, well, if I put infinity in for t, then that's going to be e to the infinity. And e to the infinity is infinity. And I need to get infinity to go away. And so the only way that's going to go away if this is a negative. So I said, hey, that'd be awesome if I, factored a negative out of this, and that would change both of these signs. And now I have a negative. But do you understand his point? He's saying, what if s was 4 though, and a was 6? Well, now 4 minus 6 is a -2. And then when you multiply by negative, it becomes a +2. And now it's e to the 2 times infinity, and now it doesn't go away. In other words, it's really important that that be negative. And so You are 100% right. This is actually only true, mathematicians, and I've told you guys this before, if and only if S is bigger than A. Did I say that right, or is it the other way around? Look back up here. Did I say that right, or is it supposed to be A is bigger than S?
I think it's right.
I said it right, because I need S minus A to be a positive number so that this negative doesn't get changed back to a positive, right? So I need S to be bigger than A. So that's kind of a little caveat here.
So Doug, I just wanted to confirm with you, S is the frequency, right? Like that's what that represents.
Yeah, that's what that actually means. So we're changing it from a function of time to a function of frequency in terms of physically what just happened here, or a way to kind of comprehend this. But again, it actually doesn't matter because we're not going to leave it in this world. We're going to take it back out and put it back in the world of time anyway. And so it kind of doesn't even matter what it is for our purposes. So we just built our first Laplace transform. And in one sense, we never need to do it again.
What if the integral diverges?
Yeah, that's a problem. Like if it diverges, then this doesn't work. You have to take an improper integral from infinity to 0, and it needs to converge. Otherwise, you don't get a kind of a finite equation. And so it needs to. You're exactly right, which is why I had to get a little creative there to make that happen. Let's do something easier. There's your first Laplace transform. I'm going to show you something really quick. Doug's table of Laplace transforms. The Laplace transform of e to the at is 1 over s minus a. Like at some point, we're going to have already made this, and then we just look it up. Like we don't ever have to do it again. We say, I need to transform this, and we just look it up. And there it is. Great. Notice though, and I'm not going to show you this at length, but notice there's a whole bunch of functions here. Like I've got all kinds of stuff. Remember things that were on the other side? Remember when we had stuff like that on the other side of our last test? Remember how when it was a non-homogeneous second order differential equation, there was an e to the at sine of bt over there, e to the 2t sine of 5t. And we're like, oh, what's our guess for that? We had to like all this complicated guessing and make sure it wasn't a double root, make sure a didn't match b and all this stuff. We're going to say, nah, let's Laplace transform it. We're going to take, what we're going to do is we're going to look at a second order differential equation or a first order differential equation, and we're going to do what we've always done in algebra, which is the same thing to both sides. That's what I do in algebra, right? Yeah, I'm going to multiply both sides by 5. Yeah, no problem. There's an equal sign. That's okay. I'm going to square root both sides. More recently, I'm going to take the derivative of both sides. Isn't that what we did with equations that weren't, like we're trying to find the second, remember in Calc 1 when you had something like this, and we wanted to find the derivative, but you can't solve it for y. And so we said, well, let's just take the derivative of both sides. We've always done that. What are we going to do in this section? We're going to take the Laplace transform of both sides. That's what we're going to do. And then that's going to make our life easier. That's where this is going. So what if that was sitting on the right-hand side and we said, oh, well, I got to take the Laplace transform of that now. Well, then we need to know what that answer is, right? We got to go figure that out. Well, here's the table. There's what it is. We just need to build all that stuff. So I showed you the first one. Let's go make another one. And I'm actually going to give you a second to try to figure this out for yourself. Let's find the Laplace transform of the simplest function you could ever think of, which is just the number 1. You try this. Now I'm going to zoom out enough that so your function is just 1. Aren't there functions that are that simple? It's like no matter what you put in, you get out 1. I'll pay you $1 a day to work at my house. Come to my house, doesn't matter what work you do, you get $1. That's not a hard integral to take. See if you can pull it off. See if you can discover what the Laplace transform of 1 is. I'm just going to give you a head start. I wrote it out just in case you screwed it up, but it's like whatever the function is, just stick it in there, multiply it by e to the negative st. Notice the brilliance of e to the negative st. We need that negative sign, don't we? Last time I was able to kind of create it, but here with 1, I don't have a lot of options. So the fact that it's negative is really good. So that's part of the brilliance of Laplace to come up with this transformation. If you get done before I start talking, go Google search. Just type in, what's the Laplace transform of 1? You're probably going to get a hit on that, even though you didn't know what a Laplace transform was before today. Like, you can check and see if you got it right. All right, I'm catching up. So the integral of e to the junk. The integral of e to the junk is e to the junk divided by the derivative of the junk. Remember, we're treating s like it's a constant. I said treating it like it's a constant. It's not, it's a variable, but we're taking the integral with respect to t. In other words, we're saying, how is this changing with respect to t? So we're treating s like it's a constant, even though it isn't one. So the integral of e to the junk is e to the junk divided by the derivative of the junk. Derivative of negative st is negative s. Awesome, there it is. Now I can plug in my values for t. So when I do that, I get, again, e to the negative infinity. Again, it's the t that's negative infinity. It's really negative infinity times s, but remember, s is being a constant. And if I multiply negative infinity times a constant, it's still negative infinity. Over negative s minus e to the, well, 0. Same thing. T is 0, but 0 times negative s is still 0 over negative s. For those of you that are a little more, technically inclined, you technically can't do what I'm saying. Mathematician, like infinity is not a number. You can't plug infinity in. I'm going to erase this, but mathematicians would say that's e to the, negative k. And we're going to find the limit of that as k goes to infinity. Mathematicians are very precise about, because infinity is not a number. And so I'm, being lazy, but you've done this before. So, we've talked about that. I'm not really a true mathematician. I'm perfectly okay with writing it the way that I just wrote it. I don't need to rewrite that then. I'm just saying what happens to it as that number gets really large. I'm not thinking it's a number. Infinity is not a number. So similar to before, you would say, well, because that e to the negative infinity really goes to the bottom, this is on its way. I should say the whole thing, I suppose. This whole thing is on its way to 0, thanks to the e to the negative infinity, right? S is just there. It has makes no contribution. But the e to the 0, of course, is 1. And then you have minus 1 over negative s, which becomes 1 over s. Is that what you got? So we say that the Laplace transform of the number 1 is just 1 over s. There's our second Laplace transform table. We're making a table of all the Laplace transforms. We need to transform all the different kind of functions we've seen. What functions have we seen? Remember, on the left side, it was always a bunch of derivatives, y and y double prime and y prime. But on the right side, there was junk over there, right? Like there was e's and there was cosines and there were numbers and there were t squareds and stuff like that, right? There were functions over there. So we gotta learn how to transform all of those. Incidentally, what if that, like on the other side, it isn't always a 1. What if it was like a 7? What do you think? Just go back and relook at what you just did. What if we did this to 7? Because it isn't always. Go ahead.
Well, can't you just factor the 7 out of the integral and then multiply it at the end?
Yeah.
Integral operator.
If this was a 7 instead of a 1, didn't we say that 7 could just kind of pop out front there? And then you just proceed as you did before. You get 1 over s, but then you just multiply it by 7, right? So does it make sense that would be 7 over s? So then I guess you could say, and I don't even know if this is in the table, but you could say the Laplace transform of kind of any constant then would just be that constant over s. So again, what's the future of this? The future of this is you're sitting there with, like 5y prime plus t times y equals 9. And you're going to solve that differential equation. We've seen equations like that, right? And in the past, you went, well, let's see, can I separate that? Or is that linear? Is this a mu problem? What we're going to do is we're going to say, let's just take the Laplace transform on both sides. Well, you now know what's going to happen over here. Well, the Laplace transform of that will be 9 over s. And now we need to figure out what's the Laplace transform of this, what's the Laplace transform of that. We're going to change it so there's no more t's, there's just s's. And then we're going to find that, oh my gosh, that 6-foot prize fighter is now 1 inch tall. I can totally do it in this world. That's the idea. Just so you kind of keep in mind where we're going with this, what this is, why we're doing this, where is this really headed? It's hard to learn if you don't at least understand why are you showing us this. So let's look at Doug's table of Laplace transforms. Look at that. There it is. Laplace transform of 1 is 1 over s. So I don't ever need to do that again, right? As far as solving a problem, I don't ever need to do that again. I know the answer to that now. Now on a test, I'm going to ask you to build a couple of these. I want you to be able to build them. When I say Doug's table of important Laplace transforms, and then I give you this most holy definition right here. I say this is Doug's table just because these are the ones we're actually going to use. I stole this one from your book. And it has the same list, but it has way more of them. Notice there's a total of 37 of them there, if you will. And we won't run into all of these. And so my table's a little bit shorter. But again, notice, hey, we made that one. And we made this one. So I know a couple of these now. That's kind of cool. Whatever this means. Now I want to show you something even more remarkable or even beautiful. It turns out these last two that I just made for you, they're actually related to each other. What would you have to do? This is kind of fun. What would you have to do to make this e to the AAT statement? What would you have to do to make that become 1? What if you wanted e to the AAT to become 1? What would you have to let a be equal to?
Just let a be equal to 0, and then
If you let a be 0, if the a happened to be that, remember a was a constant and it could be 5 or 7 or 12 or 18, but what if a was 0? Well, then what does this say the Laplace transform would become? 1 over s minus 0, 1 over s. So this would become e to the 0t, which is 1. This would become 1 over s minus 0, which is 1 over s. Isn't that kind of cool? Like those are actually related to each other. So in a sense, you could say, well, I didn't even need that second one because we already made it in the first one. Now, again, that's untypical, right? Like, you know, a is not typically 0. If you look at the other side of the equal sign on those second order differential equations we solved in the last test, it wasn't like there was an e to the 0t over there, because you would just say, well, it's 1, and let's not write it down, right? So more typically, a is 5 or 7 or -8 or whatever. But that's just kind of cool, kind of neat to observe, I think. Let's make one more. And again, I want to give you a second to see if you can make this yourself. This is a little harder of an integral to take, but what if I said, let's find the Laplace transform of just t. I didn't say t squared, I didn't say t cubed, I didn't say 5t, just t itself. And again, you've seen that on the other side of those non-homogeneous second order equations. There was sometimes t's over there, t squared. So, you know, what are we going to do with that? What if we see that? Well, you should mechanically now say, and you never need to have this memorized. I'm going to put this on the test or in the notes for you, but if I did make you memorize it, you can understand that after seeing this a bunch of times, you probably could pull that off. So you say, okay, I just take the function, oh, it's t, and I always multiply it by e to the negative st and take the integral with respect to t. Because I'm plugging in values for all my t's, all the t's will be gone and I'll only end up with s's then. That's what's kind of cool about this. With e a minute ago, we were able to put them together so there's only one function, but notice it's an integral of a function times a function. You should have a bell ringing in your mind. How do I take integrals when it's integral of junk times junk? Somebody verbalize so that everybody's at least making progress.
Integration by parts.
Integration by parts. It's probably been long enough that you're like, oh no, I don't remember how to do that. We've reviewed it in this class. But one of the questions I have for you is that a tool you can rebuild for yourself? As opposed to just looking it up? Mathematicians use the word proof. Like integration by parts, prove it. I like to think of it more as like a tool. Can you build it? I don't remember integration by parts. I've taught this class 20 times. I don't have it memorized. The reason I don't is because I can build it for myself in 10 seconds. It's super easy. The derivative of function times function is product rule. So I wrote out the product rule. And so u and v are some functions of x. And so then if I go back and say, well, I'll take the integral of both sides. Well, on the right side, the integral of a derivative cancels itself out. So that's also a true statement. So then if I just solve for this guy, the integral of uv prime, I'd have to subtract that over to the other side. That'd be uv minus the integral of u prime v. This is integration by parts. This is what you would see looking it up on a sheet. Are you a person that only you look these things up and have no concept of why they work or how they work? Or you're like, no, that makes total sense to me. I understand where that rule comes from. I can make it from scratch. And by the way, I just showed you the Laplace transform. Do you understand where that comes from? The answer is no. Like I didn't show you how to build that. It just came from nowhere, right? We'll get there. You got to see the power of it before you can be impressed with it. So then I'm going to say, okay, cool. If that's true, really what we're saying with integration by parts is if you're sitting here trying to take this integral, and the reason I'm pointing this out is it's so related to what we just did. You're sitting here staring at this integral and you're saying, I can't do that. Well, what if you changed it to this? What if you transformed it and did this instead? Is that any easier? That's kind of what a Laplace transform is doing. We're sitting here with, well, I guess we're saying this is kind of the u and this is the v prime. And I'm saying I can't do that because it's like product rule backwards. It's two things multiplied. I can't do that. And we couldn't do it a minute ago with E, right? With E, didn't we have junk times junk? Oh no, junk times junk, that's not good. What did we do? Well, we said, hey, fortunately, we can actually put those together so that it's just one E, and then we didn't need to do integration by parts. We made it into just the integral of one statement. So thankfully that was possible. What is possible down here? So let's see, well, if that's u, then u prime would be equal to 1 because the derivative of t is 1. The integral, so that I know v, because these are all my ingredients, like these are the ingredients for what I'm doing down here, right? I need to know all those things. So if v prime is e to the negative st, then I need to take the integral to get rid of the derivative. So that would be e to the negative st, but divided by negative s. So I'm sitting here with the integral of t e to the negative st, and I'm thinking, I'm too dumb, I can't do that. Well, let's transform it to something else. U times v, well, u is t, v is e to the negative st over negative s. Would you agree that's tremendously ugly, but why do we not care?
You don't have to take the integral of it.
We don't have to take the integral of it, it's done. Now what we do care about is what's coming next. The integral of u prime v. Well, if u prime is just 1, and then v is negative st over negative s, have we achieved anything? Like, have we transformed this difficult integral into something a little bit easier? Have we taken the 6-foot prize fighter and made him an inch tall here? Yeah, we have. It does not have two things anymore. And so you could say, this. Notice I can pull that negative s out front because it's just a constant. And now I can actually take that integral. So do I not get this? So the integral of e to the junk is e to the junk divided by the derivative of the junk. Dividing by negative s means there's now another s over here. So what's wrong with what I just did? I made a simple mistake on purpose.
Needs to be negative.
Didn't I divide by negative s? So this is a negative. So there, I took the integral. I did it. Except now we have to, now that the integral has been taken, we now need to evaluate this from t is infinity to t is 0. Again, the beauty of this is because I'm taking the integral with respect to t and I'm plugging in values for t, then all the t's are going to be gone and there's only going to be s's left behind. Can you stare at this and go, I'm really happy to see this? And by the way, couldn't we even factor e to the negative st out and like put those together if we wanted to? Sure, we could. I think I'll leave them alone. I don't know why. But we're happy to see that, right? Because if I plug infinity in, then I'm going to get negative infinity over s times e to the negative infinity minus 1 over s squared times e to the negative infinity. And then it's always minus. And then I'm going to put t as 0 in. So I get 0 over s e to the 0 minus 1 over s squared e to the 0. What mistake have I made there? Again, another dumb algebra mistake.
Second set of terms is being subtracted from the first one.
Yeah, like I'm subtracting all of this. So that second negative sign is actually going to get changed to a positive. Do you agree with that?
Yeah, and I guess you'd say both those would be positive signs now.
Yeah, so yeah, and so this is a negative. So there's a negative there. I didn't write that in there, which is actually just an actual mistake. So you're right, those are both going to be positives. Now let's evaluate what we have. This is a little confusing. Notice we have competing infinities up here, by the way. This is not good. In other words, this is actually negative infinity. I'll just rewrite it as s over e to the positive infinity. Isn't that right? Like if I, take this e to the negative infinity and move it to the bottom, that's the strength. That's what that negative is doing, right? So now we have infinity on the top and infinity on the bottom. Now it's up to you, Math 253 people. What's infinity divided by infinity? You might say, it explodes, doesn't work. You might say it's 1. Infinity divided by infinity is 1. Math 253 people, do you have anything to say about that?
I don't remember fully, but I don't think it's good.
Is that indeterminate form?
And this is a place where, mathematicians are a little more precise, because really what we're saying here is what is the limit of negative h over s times e to the h as h gets really big. So let's just start thinking about that. Like this is, say, 7. No, it's 25. Oops, there wasn't an e on the top. It's now 25. You should be able to see it happening right here. 25 over e to the 25th.
Oh, it's going to 0 just a little bit slower than what we've been dealing with before.
Yeah, the top is growing, but the bottom is growing way faster. 25 over e to the 25 is already pretty much 0. I'm not even sure your calculator would tell you the answer to e to the 25th.
Does it matter that it's negative?
No, because it'll be -0.
All right.
Otherwise, it would matter.
How would we show that? Like, would we have to use L'Hopital's rule? Or
Yeah, and that's again what I'm showing you here is not inordinately proofy in the sense that we're just kind of seeing that it really is on its way to zero. But it does kind of demand a proof, doesn't it? Again, that's kind of the separation. But yeah, L'Hopital's rule is a possibility. L'Hopital's rule said, hey, if you got a fraction, if it meets certain conditions, then you can actually take the derivative of the top and the bottom, and then the limit will still be the same as it was before. And because the derivative of t is 1, then maybe that'll, take infinity away on the top, and maybe it'll, so yeah, it requires proof. So
are there ways, are there circumstances where the Laplace transform just doesn't exist because there's like a divergent integral?
Yep, that's right. It only works in certain cases. You probably didn't spend a ton of time with this in 253. I didn't spend a ton of time with it when I taught it. It's a very special case. It works in certain circumstances, and sometimes it doesn't work. And so yeah. But I think you can at least see that this thing is indeed on its way to zero. And I think you can also see why it sometimes is important to write it this way. Do you see that? Like if I just say infinity over infinity, doesn't it feel like, then I don't know. But if you actually watch that value get bigger and bigger and bigger, then maybe it is a little easier to see that that's what's happening. 1,000 over e to 1,000th power is on its way to zero. This does approach a limit. And again, we're happy to see that, right? Because we need a lot of this stuff to go away, don't we?
Something that concerns me about this is like, I guess I'm not sure if it would make a difference because it would just be, I guess, a constant in this case, but we would have that s be multiplied by that it would be e to the s times h on the bottom, or e to the s times infinity, right? Not just the
yeah. And again, we're treating s like a constant, but you're right. Like what if s was like e to the -5 infinity or something? You see what I'm saying? Like if s became a function that could kind of defeat what we're seeing here, then that'd be true. So it is important to note we're sort of saying s is some function. But again, there's details to this, but the concept that if I'm treating s like a constant as a part of this integral, and then the rest of it's on its way to zero, that's at least worth recognizing. And doesn't the same thing happen with this? In other words, the next one up here, switch back to blue, is minus 1 over s squared, but then that e moves to the bottom. And so for the same reason, this one is on its way to zero because of the e to the infinity, as long as s, doesn't get out of control, as long as s isn't some crazy function. And let's keep going. Switch colors. So this would really be a plus. So what happens to this one? So we have 0 over s times e to the 0. Well, this is on its way to 1. But you have 0 over s. And so this whole thing is on its way to 0 as well. Do you agree with that? But what about this last one? This last one is minus a minus. It becomes plus 1 over s squared, but it's times e to the 0, which is 1. Hey, that actually produced something. So apparently the Laplace transform of the function 1t, and think of that as like a line. This is like, if it had been t plus 3t plus 6, it's kind of like, so this is a line. It's a really simple line, slope of 1, y-intercept of 0. That actually is just equal to 1 over s squared. That was fairly complicated, but notice that is listed right here in my table. Like that was complicated, right? And again, I didn't prove all the kind of maybe some of the subtleties to that. But I gave you enough that I think you can see that it's working.
So if we encounter a situation where the integral diverges, how should we say that like the Laplace transform of the function doesn't exist or
Correct.
that-
That's right.
cool. Nice. Will we encounter that or will it usually go away?
That's a good question. The answer is it'll go away, and that's because of the brilliance of Laplace throwing that negative right there. So we really have negative t there. And so when we put infinity into that, that part of it is going to regularly want to go away. Although, as you saw when I created the very first one we did, I had to be a little creative because that negative did want to go away, didn't it? I had a minus s times t. There wasn't a negative anymore. So that negative is really important. So it's there, and usually it will take care of the problem. Now I want to show you something kind of cool. Take a look at this pattern right here. Do you see what that second one is saying there? That's saying, what if t wasn't raised to the first power? What if it was like t squared? Didn't we have in the last test the gobbledygook, and then on the other side was like t squared e to the 3t, stuff like that? And didn't you say, oh yeah, I know what to do for that. I know to guess. I'll guess for this at squared plus bt plus c, and that will all be multiplied by e to the 3t. And so that was kind of our guess. We said, well, we'll guess that, and then we'll take its first and second derivative, and then we'll figure out what a, b, and c are by forcing it to work.
Don't forget
So-
your auxiliary equation.
I'm sorry?
Don't forget your roots.
Yeah, so that was complicated, right? Well, my point is there could be a t squared on the other side, so don't we need t squared? Well, what is this? What is this Laplace transform telling you t squared is? Oops, that didn't work. This is saying, oh, n is t. Well, on the top is n factorial over s to the 2 plus 1, so that'd be 3. So 2 factorial means 2 times 1, so it'd be 2 over s to the third. Does that make sense? Now, did that work for this one up here? In other words, if I put a 1 in, then this formula says 1 factorial on the top, and then s to the n plus 1. Well, if n is 1, then that'd be 2. Oh yeah, it did work. 1 over s squared. And so in a sense, this works for everything. Does that make sense? T to any power, even if n is 1. And of course, you might wonder, does it work for fractions? Does it work for negative numbers? What if that was t to the negative 7? That kind of, there's some questions here, but that's just interesting to note for now. What if, looking back at our note sheet, what if we did this same problem here? I'm going to erase this, but what if, those of you that really remember your stuff, what if this was a squared? How would we have taken the integral of that? Because remember, we took u prime and that t turned into 1 and it went away, right?
We would have had to integrate by parts twice.
Brilliant. Which is not fun. You agree with that? And if it was a cube, we'd have to integrate by parts 3 times. And so I'll leave that to you. Like, we're not going to build any more than this, but I do want you to think about this. If you had to take the derivative, let me erase this stuff so I don't get confused, or I'll leave my notes confused. But if you were doing integration by parts, I'm going to erase this, and this was t cubed, you'd have to do integration by parts 3 times. And when you did that, wouldn't you, if you called this u, wouldn't u prime be 3t squared? And then in the next time down, if you called this u, then wouldn't u prime be equal to 6t? And then if you did it one more time and you called this u, then wouldn't u prime be equal to 6? Where did that 6 come from? What did you actually end up doing with that 3 right there? Didn't the 3 come down front because of the power rule? And then the 2 came down front. And so you end up going 3 times 2 times 1. Do you see where the factorial came from in that solution? Just want you to have a rough feel of it. I would highly recommend you go by hand, take the Laplace transform of t squared. But you got to be, good, because it's like you're going to have to do integration by parts twice. That's no joke. But you should, you know what the answer should be now. So stay at it until you get it right. Let's do one more. So I think I'll just write this in the notes. Turns out that the Laplace transform of t to any power is equal to that power factorial over s to the n plus 1. So it's kind of interesting. I mean, just stop and think about this for a second. Like, you were working in a function of t, which is just linear. And yet when you changed it to another world, notice it became way worse. In other words, was just t, and now it's s squared. And it's not even just s squared, it's upside down. So it's like a rational function, but it's a parabola. Like, doesn't that seem like a bad idea? It's like you tried to transform the 6-foot prize fighter and then they turned into 12 feet. Like, we went the wrong direction here. That doesn't seem like that's going to be good. Now, let's do one more. What is the Laplace transform? What's the only function that we haven't fooled around with that sometimes was on the other side of the equal sign in the last test when we did second order differential equations? What else was over there? There were t's, there were constants, there were e's, and what else?
Trig functions.
Trig. And again, of course, b is constant. What we're trying to do here is not do this for, we don't want it to be sine of 5t, right? We want it to be sine of 5t or 4t or 8t. We want that to be any number. So we got to remember b is a constant, treat it like one. But again, I want to give you a second to write this out. This one is not good. This is really not good. I should probably write parentheses around that, even though you probably understand that. So you take simple, you take the function, whatever it is, you always have to multiply it by e to the negative st, take the integral with respect to t. Great, but why is this really not good? This is not a good integral to have to take. Why?
Because neither of those functions their derivatives kind of repeat iterations of their previous function.
Exactly. So when that function was a t a second ago, its derivative became 1, which means it disappeared. But if you do this with sine, it's not going to disappear. The derivative of sine just turns into cosine. And then, to David's good point, if you did it again, cosine would just turn back into sine again. So it's like it doesn't get any simpler, and neither is e. E to the junk, the derivative is e to the junk. And so the brilliance of integration by parts was you took what used to be function times function, and if you did integration by parts enough, then the two functions became one, and then you could actually finally take the integral. That's not going to happen this time. You saw this back when you were doing integrals, Calc 2. Anybody remember how this, at least how this works out? Like, there is a way to do it. Now remember, one of your options in the modern world is just to get on Google, right? And say, what's the integral? Like, type that in. I showed you all CY math. That's an awesome one. Just go in and ask it, what is the integral of that thing? I'm going to do it just because it seems like fun.
I would just go onto your note sheet and look up the
Yeah, you got note
Okay.
sheets now. Don't you have tables, right? Like you have tables. Isn't that what we're doing right now? Is we're making tables of integrals? That's exactly the idea here, and that's why I'm pointing this out. This one is so complicated that like you want to do it once and never do it again. Does that make sense? I don't want to do this again. And so let's do it once. Let's write down the answer to it. Let's make a table of these integrals and not do it anymore, right? So let's see. CY.
Is there a way to integrate that with things?
Oh, yeah,
we know
we're going
how
to do it. Yeah, we're going to do it.
Oh, okay, cool.
Yeah, I got worried when you said, let's do one more example.
You're like, it's 9/16. Integrate the sine of, I'm just going to say 3x e. Well, what are we going to do with that s? Does that make sense? Like, e raised to the -5x. E raised to the -5. I like how it lists below what you think you just typed. And then I'm not total, just to make sure, you know, so great. So I say, yeah, that's what I want. All right, I love it. Said it couldn't do it. I'm actually happy to see that. I was under the impression that CY math was just nailed everything. I like it. Interesting.
Is it? Do you maybe need more parentheses in there, like around your 3x?
I did put parentheses
did
around
put-
3x and it didn't
did,
seem to
yeah.
like it.
You did? Oh, I just glanced at the top and it didn't have it. But I mean,
Yeah, I noticed it. I noticed when I added it to the bottom, it didn't add it to the top, which is
Yeah.
kind of interesting. So let's see, just for the fun of it, basic trig identities, integral table. So let's see, I like the way these are done. It's like rational types. So ours wasn't rational. Ours had trig in it. Let's see, is this in here somewhere? We need some trig and some E. Looks like we're getting warm, doesn't it? Aha. 95 is close. No, 96. 96 is it. Do you agree with that? You guys see that okay? Do you agree that 96 is exactly what we're looking for?
That looks like it.
So our B is -s and our A is, well, A, I guess. And so notice, woo, look at that nasty business on the right side, man. That's horrible. So we could just cheat and write that down. And then evaluate it from infinity to 0. Except for, we'd have -s. Now again, notice that'd be e to the -s. And so that's good because that's going to make the infinity kind of go away. But then, woo, look at all that nonsense over there. It's like, this is kind of terrifying. So let's just see if we can make some progress and do it ourselves. Again, the goal is to ultimately know the answer to this thing, right? Like we got to build this once, but let's not ever build it again. Let's make this table and then use the table from then on. So if I'm ever trying to take the Laplace transform of both sides and I see something ugly like this, then I'll just write down what it is. I made it once, let's never make it again. Come on, screen mirroring, what's going on? Share. I think we're cooperating now. So I'm going to pull up my Laplace transform table again before we wade into this. Doug's Laplace table. Would you agree? Is that what we're looking for? Is that, I kind of forgot what we did. Was that it? No, just B. Just all we did was sine. There it is. No, that's T times sine. There we go. This is the one we're trying to make. So I just want you to note that. The sine of junk. I think I used B instead of A, but the sine of junk is, well, that. a over s squared minus a squared. That's what we're trying to get here, right? That's what we want as our answer. Apparently that's the answer, right? See if we can make that happen. Since my table wrote it the way that it did, I'm actually going to go back and use the same letter. Okay, let's go. So it turns out you do the same thing. And so I'm going to call this my u. I'm not really sure which one to pick, and I'm not sure if it matters. I'm going to call this my v prime. And so that means the u prime would be a times the cosine of at. Some of you screwed that up on the test. Chain rule.
I remember this.
Derivative of sine of junk is cosine of junk times the derivative of the junk. And we already saw earlier that v was e to the negative st, but then divided by negative s. And so I have all my ingredients for my first statement. So I'm going to try to write this out so that you can see this. And I'm going to save space by not even putting dt in there and putting nothing else. And so we're saying, I can't do that integral, right? I'm too dumb. So I will transform this, thanks to integration by parts, into a new one, u times v. So that is the sine of at times e to the negative st, all divided by negative s, which is horrifying, but I don't have to take its integral. Again, tell me if I do something stupid here. Minus the integral of our new statement, which is u prime v, a cosine of at v, e to the negative st over negative s. What's your thoughts on that? Okay, we transformed it. Is that better?
No.
No. We made no progress whatsoever. Do you agree with that? Now, it would seem like, you know, bad idea, like don't do this, like go try something else or whatever. But it turns out this is actually going to work. Let's keep going. Now, can I make one switch here? Would you agree that this is a constant, a over negative s, and so I could pull that out front, and then the negatives would cancel, and so there'd be an a over s out front? You okay with that? And so would you agree this looks almost identical to what we started with? Like, what did we start with back here? Well, we had the integral of sine of at e to the negative st, and now we're sitting here with the exact same thing, except for it's just cosine. So it's like, well, that was a big waste of time. That didn't really accomplish anything. Yet, we're not going to quit. Oddly, this is actually going to go somewhere. Again, you should I want to say you should kind of know this. You've seen this before, but probably
Don't you cancel out the entire integral?
Yeah.
Right. Yeah, like they add and subtract together.
So if that's u, if we kind of do it again, which again should feel foolish to you, then you'd say, okay, well, the derivative of cosine of junk is sine of junk, negative sine of junk, times the derivative of the junk. So there's u. And then this is still v prime, and so that hasn't changed. I'm not going to even rewrite v. And so then we would say, okay, well, what do we have now? Well, we have all of this. I don't think I can ever do this without a computer like this again. It's so awesome. And so now I'm just going to replace, well, this part. So the integral of cosine of junk, we're saying, what does that become? It becomes u v, which is cosine of at times v, which is e to the negative st over negative s, minus, and then this new integral that we're hoping is going to be helpful, right? We're hoping this brand new integral is going to be easier because we failed the first time. So it's the integral of u prime v, but what's u prime? U prime is negative as sine of at, and v is still e to the negative st divided by negative s. And so you should say, well, that was a dumb waste of time because it isn't any easier. Not only that, we just chased our tail in one complete circle. Do you agree that we're right back where we started from? And now we need to take the integral of sine of at times e to the negative st. We're back to trying to do the same exact thing that we did before. So this is not working. Do you agree with that? And remember, all of this is still multiplied by a over s. So let me write out what we've got now. So plus a over s. Notice it's multiplied by negative s though, so now we have another one, and then that would become a negative. So all I'm doing is distributing this as into that cosine of junk. So then we have the cosine of at e to the negative st, right? And now I'm going to distribute this as into this junk, except for notice there's a negative sign here, and then these are both negative. So that's actually positive a over s, but then it's negative. So if I pulled it out front, that'd be minus a over s multiplied by a over s. So did I screw this up? Help me not get this wrong. So isn't it minus a squared? Oops, that's not squared. Minus a squared over s squared. And then there's still the integral of sine of at e to the negative st.
Yeah, I think that's right.
Now, do you agree that that doesn't appear to be working? Because I still have an integral I can't take. Not only that, I'm back to where I started. But what's brilliant here that I can now do? I'm almost done.
You're going to cancel out the integral from both sides.
Yeah, what if I added this away from the right side and added it to the other side? Would you agree the other side, because there's really one out in front of this, would really be 1 minus a squared over s squared times that integral? And the right side would be unchanged. Again, this is just algebra, but that's no good. Doesn't quite fit. I'll just scoot it over here a little bit. Do you agree that's what would happen? Algebraically, if I added that to the other side, oops, if I added it, this would be a plus sign, right? And so we're actually going to succeed in taking the integral of sine of at e to the negative st and never have to take it, because all I need to do now is divide both sides by that 1 over as squared business. So the integral of sine of at e to the negative st is all this junk that's on the right side. But then I would just have to divide by, and I'm going to find a common denominator for that so that I have s squared plus a squared over s squared. You okay with that? I just took 1 and multiplied it top and bottom by s squared so that I just have one fraction. I mean, isn't that kind of cool? Like we actually never were able to take the integral of it yet because it chased its tail and got back to the same exact integral. We're able to add both sides. Huh. It's kind of mind-blowing. Now, of course, that looks tremendously awful over there, right? But remember, the integral that we're trying to take, we're saying we just got done taking it. Remember, we're supposed to plug in t is 0 and infinity, which means I have to come back here now and put in infinity and 0 for this and see what that becomes. Do you agree with that?
Yep.
Whew. So let's put infinity in and put 0 in. What happens if I put infinity in here for t? Well, that's going to move it to the bottom and become e to the infinity again. Do you agree with that? What happens to the sign of infinity? Now think about what happens to sign as you cruise around the unit circle. What kind of values do you get when you take the sign of 7, the sign of 19, the sign of 52, the sign of 65, sign of a million? Remember, t is a huge number, but when you take the sign of a number, what kind of numbers do you get?
Aren't they getting smaller?
You only get numbers between 0 and, between 1 and -1. Isn't that right? They always stay between 1 and -1. Doesn't matter if you take the sign of 50 million, you're still on the unit circle somewhere. Think about the sine wave if you want to. You get numbers between 1 and -1. So you're effectively getting, I'll go ahead and write this out, the sine of, I'll just say infinity, since t is infinity, over -s e to the infinity. Is that what you're getting? This is between 1 and -1. So that's going to stay a small number. And we don't care whether it's positive or negative because e to the infinity is causing the bottom to be infinity. So think of it as like -1 over infinity. I mean, this is on its way to 0. Do you see that? So this whole thing is going to be on its way to 0. What happens with the next part of this? Well, isn't it the same? So you have a over s squared, which are both just constants. But then you have the cosine on top of infinity, and on the bottom you have e to the infinity again. So this is also on its way to 0. That's actually good news, right? Again, that's the brilliance of the Laplace transform. Thank God for that negative sign, right? It's a good thing that was e to the -s. Now, it gets more interesting when 0 is involved. And notice, by the way, like I have left off here the denominator. Don't these have a denominator underneath them? But since they're both 0 over, some constant, 5,000 or whatever, is still 0. But what happens when you put 0 in? Let's slow down a little bit. So let's see, sine of 0. So you have sine of 0. And then you have e to the 0 over -s. What happens to that term? What's the sine of 0? Should be able to see that in your mind on the unit circle, but if not, bust your calculator out.
0.
0. So e to the 0 is 1, like that's cool, but sine of 0 is 0. So this is on its way to 0 too.
It's cosine of 0, that's 1.
Exactly. We're about to get an answer because the cosine of 0, so this last one, and notice it's a minus sign here. And since we're subtracting, that'll actually become a plus sign. Isn't that true? So it's a over s squared cosine of 0 e to the 0. That's actually going to produce something, is it not? Cosine of 0 is 1. E to the 0 is 1. And so we actually just got an answer. We got a over s squared. Except don't forget about this. Like that's down there too. So then I guess we have a over s squared. How do you divide fractions?
Multiply by the reciprocal.
I teased a bunch of you about this before, multiplied by the reciprocal. Rad. Bam. Bam. The Laplace transform of the sine of any number times t is equal to a over s squared plus a squared. Now, whew, I'm really hoping I got that right because that seems awful complicated. Sweet. Let's not do that again. Let's write that one down, right? Notice cosine doesn't kind of make sense that cosine would be related, but isn't it interesting that it kind of leaves an S on top instead of an A on top, but it's almost the same. That's kind of cool.
That is kind of cool.
So, you know, those of you that are curious people should feel like, man, I want to make that, or maybe I could go back and look at what I just did with sine somehow, and, you know, maybe not have to redo the whole thing. I don't know, but it's like,
What does tangent look like?
let's see, what does tangent look like?
Is it on there?
Huh. Tangent doesn't seem to be on there. Wonder why that would be. This gets at David's point earlier, like, can you take the Laplace transform of everything and get a finite answer? The answer is no, you can't. You may have noticed we had trig on the right side of our second order differential equations. We never had tangent. We never had logarithm, right? I gave you more time to do the project yesterday, but the third method on your syllabus, 4.6, is called, I forgot, so I'm looking, variation of parameters. That's another technique that I didn't show you that does allow you to get more problems right that you weren't able to get right before. And again, Laplace transform will take care of that automatically, but it's no accident that tangent's not on here, which means when you try to take the integral of tangent involved, you're not able to be successful. The derivative of sine turned into cosine, which turned back into sine. Isn't that how we survived this? But the derivative of tangent is secant squared, and the derivative of secant squared is secant tangent, and it just gets worse and worse and worse. And so, like, you don't get anywhere with the integral of tangent e to the negative st. And so now, the reason I called this Doug's table of important Laplace transforms is I've made every one of these. I've made them. I own them all. Like, I can do them myself. I built them all myself. I would encourage you to have your own table of Laplace transforms. Like, make them all. Now, do you have to? No, you do not. I'm not going to ask you to make really hard ones. I can't ask you to do what I just did on the test. I can't say, at least it doesn't seem fair to me, I can't say, you know, build that, right? That's a pretty big ask. But I could say build one of the easier ones, right? Like t, that Laplace transform of t, or Laplace transform of e to the at. I could ask you to build one of those on a test. I will be asking you to build something simpler on a test. So that'll be part of your grade on this next test. So you should have your own table of these. You should build them all, build a bunch of them. You can probably appreciate this one apparently is going to be horrible, right? Not only did that have a sign in it, but it even has an E in it. Like, how hard would that be? Like, that just seems awful. And so, you know, we've got to talk about some things, although you might notice that this doesn't look terribly different than what we just did, but we'll get into that later. But can you see where we're going with this? That's kind of where we are right now. Can you see that if I have some of these, and notice we actually have a lot of them now. We kind of have this many of them. We have those, we basically understand those. We understand this one, and we could steal that one. We sort of understand where that one came from. We don't really understand the one that I didn't circle. So does it make sense we're on our way to being able to handle the stuff that was on the right side of the non-homogeneous second order differential equations we just did? What we can't do now, what we don't know how to do yet, is what's the Laplace transform of a derivative? What's the Laplace transform of a second derivative? Tomorrow I'm going to build those for you, because that's what's on the left side, right? And once we can take the Laplace transform of both sides, then we're going to, you know, see that beautiful things happen. I want to caution you, this is really cool in the sense that this is a way to not have to think as hard about what technique do I use, but it's by no means simple. It doesn't just make this suddenly easy. Still kind of challenging, but it's a really cool technique. So the last thing I want to say then is this. I'm going to post this. I don't know when you should watch this, but you should definitely watch this. This guy, Arthur Maddock, is an MIT professor, and I just found this online. This isn't, there's probably better videos, but it's like 2 5-minute videos on where this weird Laplace transform comes from. In other words, why you're taking a function and you're suddenly multiplying it for no reason by e to the negative st, and then you're evaluating it from infinity to 0. Like, what? What? Because at this point we haven't used it for anything, right? I've successfully shown you, I think, that you can transform something from one world to another, which is something you've done before with substitution. But like, why? Who cares? And secondly, you know, where does this actually come from? He does it. It's a really pretty masterful job, I think, of, and it's really awesome because it has to have been done like in the 80s, because he's literally writing on the chalkboard with some chalk. And you know, it's like somebody with a video camera out in the audience, and so it's kind of old school, but there's something about it I kind of like. But he does a really good job of explaining how it really is just a power series. And again, if you took 253, then that makes sense. I actually don't think I would bother watching this if you didn't take 253, because he alludes to a power series and how really this is just the culmination of a power series. So if you want to, and honestly, I probably would recommend you watch this maybe over the weekend or maybe like Tuesday or Wednesday next week, because at this point you don't have much of a sense of, you know, like what this tool is and what it can do and so forth. But again, what the reason I think you need to watch this at some point is this wasn't just random. It wasn't just accidental. So let me just show you this and we'll be done. Let me see, is it still sitting in here? So this is something I shared with you before from 253. So that's a power series expansion for.
Oh, I remember staring at this page.
Yeah. And we used it again, like we brought it up in this class because it allowed us to make I disappear from our auxiliary equation answers. When we got an imaginary answer, we were able to make it go away. But I only remind you of this because I really do want you to watch his explanation, and it won't make sense unless at least you have a sense of how this works. But e to the like 2, like let's say you wanted to know what's e to the 2, and keep in mind this is like what people that you and I, we have a calculator, we break out e to the 2 and it's like there's our answer. We sort of, you know, act like, well, it's easy, but it's like your calculator is a machine that was built for you. And so, you know, it turns out that that's the same as 1 plus 2 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4th over 4 factorial. Like, that's a power series expansion. Power series is, this is x to the 0, this is x to the 1, this is x to the 2, this is x to the 3, x to the 4, x to the 5, x to the 6. Those are powers. That's what's called a power series. And then notice the coefficients, if you will, are factorials. So this is really 1 over 1 factorial. This is x to the 0 over 1 factorial. I'm sorry, 0 factorial. This is x to the 1st over 1 factorial. This is x to the 2nd over 2 factorial. Like, they're all the same exact. It's not like the 1 and the x are different. But anyway, that's the power series. And he kind of shows how this came from the logic of a power series. So it was built. It wasn't just stumbled upon. Again, I like to think of that, you know, you're out in the woods and you stumble upon something like, whoa, I just found something cool. I found a cave. You know, it wasn't that I was smart. I didn't know there was a cave. I just stumbled upon it. No, mathematicians built this. They made it as a tool that would do a job. And it's literally comes straight from the logic of a power series. Again, an illustration I like to share a lot. You could get your telescope out and just kind of look up into the night sky and you might discover a planet. Like if you just happen to be looking at the right location in space and you had the right focus, you might actually see something out there that no one's ever seen before. You'd have to have a better telescope than any of us could afford. But mathematicians actually found the planet Pluto not accidentally, but mathematically, because planets around them that they could see weren't flying like they should be flying. They were flying as though something was out there gravitationally that was knocking them off course, if you will, because we understand how, thanks to algebra and math, we understand in physics how planets behave, how gravity works. And so this one planet wasn't behaving correctly. So they did the calculations. Well, in order for it to move that way, there would have to be a planet about this size in this location. And then they went, hey, look, there's Pluto. Like they didn't discover it accidentally. They found it based on logic. And so the video that I'm referring to you to is explaining where this comes from. You might have to watch it twice. You might have some questions for me, because you do have to have a foundation in infinite series a little bit to make sense of it. But he does a great job of just literally building that. So it's kind of cool. Okay, let's uncharacteristically stop right there. And I would recommend you do your 7.2 assignment tonight, because we're going to go on and do this for other things and begin to use it. So, you know, if you have time, if you can at all pull it off, I would recommend the 4, 6, 16, and 18, the 4 questions that I assigned, because then we'll start building stuff tomorrow. Okay, so the rest of whatever time you want, you can either ask me questions about things, or I'll stay here as long as you want if you'd like to go over anything on your test. And I say that for 2 reasons. One, because you might be arguing for a few points that maybe you don't think I caught, which I'm 100% open with. Or more importantly, there's a few things you didn't understand or you didn't get right. And you want to understand them so that there is a final in this class at the end. So let's make sure you understand it. So
for the homework.